So yes, we're getting back to microbes. So it's a quite different topic. Cyriane, you've got a big task to follow.
Yeah, a big challenge. Okay, so I will invite the speakers to directly come, and you can sit there on the chair. So hello, I'm Cyriane Fournier. I'm a chemical engineer, and I have worked for 10 years now in Geostock. And today I will host the panel discussion about impacts of microbiology in the underground storage. So this morning we had a presentation about what have been done in Hystories project. So we have characterized the reactivity of hydrogen in underground storage. We have assessed the consumption rate of hydrogen with bacteria, in contact with bacteria. We have also presented some first modeling that were developed, and also presented some mitigation solution that could be considered. And so now it is interesting to draw a parallel with what have been done in some other projects. So we have 3 specialists with us today. And so each of them will present you what they have done in terms of microbiology and geochemistry in their project related to decarbonized fluid. So it's not only hydrogen, but we will talk also about oxygen and or CO2. And then after we will exchange together about some technical challenges that are still necessary to solve for this topic. So I will first invite Anne-Catherine Anne to present. So maybe you can sit there or to pass the slide. So Anne-Catherine did her bachelor and master at the University of Liège in Belgium as a bioengineer in chemistry and biotechnology. Then she did her PhD at the University of Amsterdam, where she studied the stress response of a genus of alloalkalophilic, it's like supercalifragilisticexpialidocious, sulfur oxidizing bacteria from soda lakes. And since February 2022, she works as a postdoc in the HyUSPRe project at the University of Wageningen. Thank you.
Thanks a lot. Yeah, well, thanks a lot for the introduction, and thanks a lot that we can share our results here with you. So I will share our results from the HyUSPRe project, but also we have another project in our group, on the microbial impact on hydrogen storage. Oh, this was the wrong direction. Nope. Ah. Okay, so here's our team. So we are supervised by Diana Souza and Bart Lomas. And as I said, we have 2 projects in our group. So the HyUSPRe, where Diego and myself are working, and HyUSPRe focus on porous reservoirs. And then we have the HyStar-React with Adrian, and this project focuses on salt caverns, and we have also samples from porous reservoirs, but mostly salt caverns. And then Ton is our technical support for both projects. Just wanted to give you a little overview of the HyUSPRe project. So we have multiple work packages, 7 in total. So the first one did already the map of the hydrogen storage capacities, the transport, the usage and the production Europe-wide. And then the 4 next work packages were more the interactions with hydrogen and the reservoir. So first, of course, the geochemistry. Then we have the microbiology. Then we have the flow behavior of hydrogen within the reservoir. And last, the integrity and the durability of the reservoir and the well, also especially with the cycling of the hydrogen, so injection and retrieval, but also corrosion is included in this work package. And then work package 6 will summarize all the data we obtained from the 4 work packages above, and will introduce them into a multi-scale modeling system. And we hope with this modeling system we can give an estimate of the hydrogen which is retrieved, so the quantity, but also the quality. So if methane or sulfide are produced and are contaminating this hydrogen. And then the last point, the work package 7, is to make a technical assessment of the hydrogen storage capacities in Europe and also give a guidance for this. So this was for the HyUSPRe. So coming back now to my favorite topic, the microbes. So one could think in this subsurface environments that there's no life possible because we have these extreme conditions. We have the high temperature, we have the high salt, we have limited nutrients, we have limited energy source, so it's actually not so much food also there for them. And next is also, there's not a lot of size, pore size. Actually the space which can be colonized by the microorganisms is not a lot. But despite these facts, the microbial composition is 2 to 19% of the Earth's total biomass, so absolutely not neglectable. And the cell numbers can reach from until 100,000 to 1 million cells per gram of rock. Of course, we decrease with the depth, and it's also depending, of course, on the environmental conditions. But in a nutshell, we can say that life is possible until around 5,000 meters. Until then, we cross then 122 degrees threshold for general life that can be supported. But what has been known is that most microbes are, due to this extreme condition, in a dormant state. So it's better not to wake them up. But this could happen if you introduce hydrogen, because hydrogen is just a super yummy energy source for these microorganisms, especially in the sub-Earth surface where there's not a lot of donuts available. So once they wake up, we can have multiple detrimental impacts on hydrogen storage. First of all, they consume, of course, the hydrogen we want to store. They can contaminate the hydrogen with other products, sulfide or methane. They can also provoke microbial influenced corrosion. And they can also, of course, develop biomass or produce sulfide, which precipitates iron sulfide. So, which in the tube, for example, can block your injection for the hydrogen. And we have, of course, multiple functional groups which can consume hydrogen. But for hydrogen storage, the three main are there. So methanogenesis, sulfate reducers, and acetogenesis. But what is really not well known is who is actually present in these reservoirs and which are also the relevant taxa in this reservoir to impact hydrogen storage. And also the second point is it's not really well known what will be the impact of this high hydrogen pressure, especially in correlation with the temperature, pressure, salinity, and the pH on the kinetics. So will it increase the kinetics if we have higher pressures, or will it decrease? So this is all questions we need to answer. So with this, I want to deepen a little bit for the VP3, so the microbiology part in this HyUSPRe project. So first, we want to assess the microbial community and composition in environmental sites. Then we want to determine the window of viability of microbes. So for this, we incubated environmental samples under different conditions, and we saw under what conditions we can grow microbes. With these enrichments, we use them for the determination of the kinetics. So we incubate them in high pressure, high temperature reactors and the different conditions. And this kinetic data is then implemented into the model, which gives then the assessment on the quality and quantity of hydrogen in the end, with all the work packages from the project. And then the next point is we want to challenge the model to verify if we have good outcome. So we'll do competition experiments where we compare under different conditions which functional group has advantages over another one. And then the last point, we will also perform case studies. So in this, we want to grow in high pressure, high temperature reactors, formation waters at the site-specific conditions. And all deliverables you can find on the HyUSPRe website. There's one example, for example, for the first task we uploaded already, and you can just download also from all other work packages. So for our environmental samples, so we obtained 29 porous reservoir samples from 4 partners, and we also have 2 salt-carbon samples from 2 partners. And under these samples, we have also target sites and also one pilot study for hydrogen storage. And it's really nice actually to work with these environmental samples because it's really the microbial community which is present in this environment and not just straight from a culture collection which might not be adapted to the real conditions. So let's start with the that site. So we have a salt cavern where for 6 months hydrogen was stored. So in the beginning and in the end, we took liquids and filter samples to check what will be the impact on the microbial community composition. And also we incubated cores. So you can see here in these balers, there's like cores were incubated. They have a spongeous structure and we hope that they accumulated like biofilms. Unfortunately, it was super oily, so we couldn't see anything so far. We couldn't analyze them yet. But we hope we can also analyze the microbial community from those. For the window of variability, so as already mentioned, there was a really nice review just in 2021 published about the window of variability of microbes from the 4 different main conditions impacting and on the 3 main functional groups. Here you can see a table summarizing those data they found in this review. And in a nutshell, they said, okay, the 2 most constraining factors is temperature and salinity. So as I said already, the known limit for life is 122 degrees so far. And second point is also, as it was shown this morning already, the graph. So as you can see, you have here this graph with the critical salt and critical temperatures is showing all pure strains, so pure isolated strains, and there are extreme conditions under which they can grow. And there's on the right corner, of course, like this white hole. So it's expected that there's no strain able to grow at under this condition. But yeah, let's see what our results showed. So first, we incubated our environmental samples under 80% hydrogen, 20% CO2 at 1.7 bar, different temperatures and different medium. So temperatures we used 35, 50, 65 and 80 degrees. And you can see A to F is porous reservoirs and G and H is salt caverns. And for the medium, so I guide you a little bit through, so sample amended with nutrients. So we took just the environmental samples and we added nutrients on top. So we hope that it conserves its initial conditions like salt, minerals, and doesn't get too much disturbed. Then we also cultivated in mineral medium. So of course there the microbes see completely the environment change. And then we have also a mineral medium with a little bit adjusted of salinity, and also we added sulfate. And as you can see, we got all 3 functional groups growing in those samples. It depends a little bit on the sample how fast it goes. So some after 4 days, some after 3-4 months, or 7 months. But the longer you wait, the more risky that someone will still come up. And also important, as soon as we added sulfate, despite the fact that those initial samples didn't contain any sulfate, sulfate reducers came up. So they're just sitting there and waiting to get some contamination of sulfate and produce sulfide. And for these samples down here, the reservoirs contained a lot of sulfate. So it was no wonder for us that also the sulfate reducers came up. So it's really important to notice this. If your reservoir already contains sulfate, you have a really high risk. And for the methanogenesis, for the acetogenesis, we got growth until 50 degrees. For methanogenesis here until 65, and sulfate reduction got until 80 degrees. We did the same just with pure hydrogen, so 100% hydrogen at 1.7 bar, again at different temperatures. And here we got methanogenesis and sulfate reduction, and methanogenesis here until 80 degrees. And then we also said, okay, let's take a sample where we have the biggest cocktail of microbes possible. So we call it master mix. It's just a mix of different inocular of relevant environments. And we cultivated them with 0.5 mole of salt and 3 millimole of sulfate, and also with 2 mole of salt and 3 millimole of sulfate. And as you can see, we obtained growth at 2 mole of salt and 65 degrees. So this is actually above the currently known limit of activity or viability for microbes. So if we want to find them, it's still possible. And it's slow. It's 2 millimole for 7 months we got now. But when I checked them under the microscope, I saw different shapes. And I sequenced them also just quick sequencing, but I got multiple bacteria, I got multiple archaea. So this 55 degrees and 1.7 mole of salt is not thus constraining, and it will be pushed further the boundary for viability. So with this, we have at least to push the boundary to 65 degrees and 2 mole of salt. But I'm quite sure this will be still higher. At the same time, we're also building up our reactor system in our lab. So we have at the moment 2 systems. So one was already there, but we needed to adapt for hydrogen because everything is more complicated with hydrogen, high pressure, sulfide production. So we have 3.6 liters, and they can go up to 70 bars. So good to work is 56. We can measure pH, pressure, temperature. This temperature can go up to 350. Stainless steel, and they get lining to be protected. And then we purchased also new systems, small reactors, 0.5 liters. They can go up to 250 bar this time, so 200 bar security-wise. And then the pressure and temperature is monitors. Again, temperature can go up to 350 stainless steel, and those go, because we bought them, we can afford also to get them in coating to be completely protected. Yeah, that's finished now. So with this, I would like to conclude. So the limits of life we found is for acetogens like 50 degrees, sulfate reduction 80 degrees, methanogens 80 degrees. And as soon as we added sulfate, we got also sulfate reducers. Either it was already present or we added it. And we can say that the window of availability shifted to at least 65 degrees and 2 mole of salt. And you can see this in the graph, how it will shift a tiny bit, so it's not that much. But I expect that this will still be pushed a little bit further. And then for the next steps, we need to determine the kinetics in the high pressure, high temperature systems, and this will be then implemented in the model, which will give us a global overview of hydrogen quantity and quality upon withdrawal. And with this, I would like to thank the hydrogen team at the Wageningen University, our groups, the microbiology group and molecular ecology groups, and all the industrial and project partners from the HyUSPRe. And with this, like you to attend, for your attention, and please feel free to ask questions.
So thank you very much. I don't know if we have the time to take 1 or 2 questions from the audience, if you have on HyUSPRe presentation. No, good. Maybe one. Yes. You can go? Okay.
Yeah, thanks for the interesting presentation. Just circling back on what was presented this morning on material selection and the cases. You have some ideas of the contaminants and the contents that could be expected, for instance, H2S in case of or the other contaminants that you've analyzed. So any clues, it traces or significant amount that could be generated?
So I can just tell you for low pressure, so we didn't start at the high pressure, but for low pressure, now I have, for example, from the test site, I incubated also, I couldn't present it because it's still running, but last week I had 2.5 millimole just with hydrogen of sulfide, and if I boost them with nutrients, I get 5 millimole of sulfide. After 3 months, and it's steadily growing. Methane can be 100%, like a complete conversion, what I see. But it's faster, methane, for my experience, than sulfide.
And I can add also from the results more on Hystories project that in terms of H2S, what we have modeled, it was more about less than 1%, so it would be 100 or 1000 ppm, but depending on the site, but we should not go above 1% in H2S.
Thank you.
Okay, Martin.
Thank you. One question, one technical question. The enrichment, did you do you intend to compare the enrichment cultures with the original samples? by molecular?
Yeah, so we took samples from the like time zero, and then at the end, yes,
Yeah, I
see
mean,
what is growing and what not.
yeah, okay. So you compare the
Yeah,
the
it's
enrichment
not
file.
possible for all sites because not everyone was able to take filter samples in the beginning, but we have sites, yeah, we can compare really from the reservoir directly after sampling, taking filters, and then after, of course, incubation, before incubation, time zero, and in the end, yeah.
That's good. How do you intend to have the reference for the consumption tests? Do you calculate per cell or per volume or
Per liter. Yeah.
per liter?
Yeah.
So that really depends on the density of the enrichment culture. Isn't that a problem for the later calculations? I mean, it's a difference.
In the model, everything is taken into account. So what will be done for the reactors is we track over time really the density, and every methane sulfide is every time tracked like after X days for the reactors for the real.
But then you have a very varying factor in your calculations. I imagine because it's a difference if you have an enrichment culture at the beginning of 1 million or only 1 to the power 4, and the conversion is different.
Mhm.
If you then calculate it with the volume, that might be a
Mhm.
failure finally.
Yeah.
So just an idea
Yes,
how to
yeah.
from the beginning to calculate.
For the models will not be a problem because it's really the kinetics, so cell growth and with consumption at the same time and production.
Yeah, but the point is that if you have
It's different, of course, if you have 10 cells or 1 million cells.
That's
Yeah.
what I mean. Yeah.
And of course, in the beginning, they have a long lag phase because
Sure.
of these kind of things. Yeah.
It's
Yeah.
a general problem. I just
Yeah.
need to.
Yeah. Thanks.
Okay, one question from the chat, maybe.
Yes, a question from the chat. Sorry if maybe you have explained it before, but so the question is, how did you collect the water samples? Was it wellhead samples or downhole samples?
Downhole.
Okay, thank you very much. And Catherine. Okay. So after this first presentation, I will invite Anthony Ranchou-Peyruse to talk about what was done during RING's H2 project. So Anthony is a professor assistant at the University of Pau and Pays de la Dour. His research activity focuses on the understanding of the functioning of microbial community in deep continental environments, and he has been working since 2009 on deep aquifers used for natural gas storage. Thank you, Anthony.
Thank you. So I'm pretty sure that now you are pretty close to be expert in deep underground microbiology. So, I hope. So I'm going to present you the RINGS project funded by Storengy and Terega. RINGS is for the name of RINGS is for research on the injection of new gases inside the deep aquifer used for storage. And so it's a pluridisciplinary project with microbiologists, process imagists, chemists, geoscientists, and so what I mean by new gases is not new gases at all. We talk about hydrogen and oxygen. So as you know, I'm not going to talk about the importance to evaluate the injection of hydrogen inside the deep aquifers, so storage. But I'm going to explain a little bit about the oxygen. So because of the energy crisis, we have upscaling of the production of biomethane. And before the injection of biomethane inside the natural gas grid, we need to reoxidize sulfide. And so we inject oxygen inside the system. And so it's possible to detect oxygen inside the natural gas grid. And the maximum of oxygen detected on this gas grid is about 1%. And so you know that deep aquifers are an anoxic microbial ecosystem. And so the question is, if we inject oxygen inside this deep anoxic ecosystem, what about the microbial community, and what about the storage? So we expected arrival of these gases in the UGS, and the three question is there a risk to the storage facilities? How do indigenous microbial communities respond? And is there an effect on the quality of the storage gas? So in our project, we built a high pressure reactor, a deformable high pressure reactor. And so this reactor can work up to 150 degrees Celsius and 150 bars. So why this high temperature is for the sterilization of the system. And inside this reactor, we have a three-phase with the gas phase, the liquid phase, and the solid phase with a rock from the targeted site. And it's a deformable reactor because we want, during 3 or 5 months of incubation, we want to do sampling each week. And so sampling of gas, sampling of liquid, and we want to maintain all the time the same pressure inside the reactor. So we need to do a movement of the piston in order to have this equilibrium of pressure. About the water, because of the question just before, we use a downhole sampler in order to have the water and the microorganisms from the deep aquifer, and we use a rock from the targeted site too. And what about the gaseous phase? We want to simulate natural gas, so we do a synthetic gas mix with methane 99% and CO2 1%, and some traces of monoaromatic hydrocarbons, benzene and toluene. So, as I said, for the water, we used a downhole sampler in order to obtain the best sample possible without contamination. And with this system, we are able to control the pressure. So we have not a strong depressurization, for example, or quick depressurization. And we are sure that there is not contaminant from the wellhead microorganisms. So we published these results. And so, in this moment, we did 5 different experiments with the injection of hydrogen, and today I'm just going to show you, to present you three of them. So for each line, it's an aquifer. So we have the aquifer 1, 2, and 3. For the first column, it's the monitoring of the gaseous phase. For the second column is for the liquid phase, and we do modulation for pH and redox in the third column. For the first aquifer, we tested an injection of 10% of oxygen. It was the same thing for the second aquifer, and for the third aquifer, we tested another scenario with 3 times an injection of 2% of hydrogen. Each time, we saw a decrease of the hydrogen and a decrease of CO2. For the first experiment, it was a school case. Everything we planned was in this experiment. So at the beginning, so we injected the hydrogen. We saw, so with the blue square, you have the quantity of sulfate. So in this aquifer, the quantity of sulfate was very, very low if you compare to the two other. And so quickly we had a consumption of sulfate, and at the moment, after 50 days, there is no sulfate anymore inside the system. And at this point, there was a methanogenesis, and a higher decrease of CO2 and hydrogen. When there was no hydrogen CO2 anymore inside the system, the consumption of hydrogen stopped in the same time. When I talk about CO2, there was a decrease of CO2, but there was a decrease of carbonate, and there was a decrease of calcite too, a dissolution of calcite, because everything is in equilibrium inside the system, and with the consumption of microorganisms, there was less of calcite inside the system at the end. And another thing important is just a few days after the injection of hydrogen, we saw the production of formate. And this production of formate is from acetogenic microorganisms. So, acetogenesis produce acetate. Oh yeah, we all agree with that. But in the same time, with the pressure, it's possible to split the metabolism and to obtain a production of formate. And so we saw this production of formate in pink each time with the different aquifers. I continue with the first one, and as we saw this morning with the methanogenesis, we can see an increase of the pH. And I think that this increase of pH is very, very important. It's because we have a consumption of CO2. I think there is some reaction, but maybe for the question after, I think it's very important because here we have a pH of 8, and so the question is, so we are sure there is a production of H2S, but H2S is for acidic condition, and so maybe if we have other conditions, it's possible to decrease this quantity of sulfide, H2S. The second point is important for me is this one. So we have a lot of sulfate inside the system. Okay, so at the beginning we have a sulfate reduction with a decrease of sulfate, and there is a stabilization of the consumption of sulfate, and in the same time we can see there is a stabilization of the decrease of hydrogen and a stabilization of the decrease of CO2. So I'm not completely able to explain what happened at this moment, but that it means it's possible to have some microorganisms able to use this hydrogen to have sulfate, and because there is a lack of something, I don't know, maybe ammonium, for example, or phosphate, there is a lack of something, and so the consumption stopped. And we obtain the same kind of results for the third aquifer. So about the diversity, all the time at the beginning of the experiment, we have a community initially dominated by fermenters and sulfate reducers. And after, we saw sulfate reduction with the consumption of sulfate, and we have some family like the ammonophycaceae, which are going to consume this sulfate. And as I said, we can see the production of acetate and formate in all the experiments. And the last point is methanogenesis does not necessarily take place, because for us we are sure that there was methanogenesis just in the first example, in the first aquifer. So since this result we worked on another aquifer, and so we saw methanogenesis, but that means we have not methanogenesis all the time on each deep aquifer used for storage of hydrogen. So just a little bit about the injection of oxygen. We did two different experiments. The first one with 1% of oxygen, the second one with 100 ppm of oxygen. So 1% is because it's the maximum quantity of oxygen detected after the injection of biomethane inside the natural gas grid. And why 100 ppm? Because it's the maximum concentration authorized today in France for the injection of biomethane inside the deep aquifer. So for the first scenario, so it's not a surprise, we have sulfate reduction, okay, so with the consumption of sulfate, and when we are going to inject oxygen inside the system, we have oxidation of this sulfide and the production of sulfate. Here it was for the acetate. For this part, we were interested by the capacity of microbial community to degrade toluene and benzene. And so we can see in this first scenario with 1% of injection of oxygen, in green we have the decrease of toluene, and after the injection of oxygen there is no degradation of toluene anymore inside the system. And why? So it's simple. If I inject 1% of oxygen inside the deep aquifer with a pressure of 60 bars, I mean I created hyperoxic conditions, and so it's very toxic for everyone here and for anoxic microorganisms too. And so, as you can see, there was a decrease of the quantity of microorganisms, even if it was still. We were still able to detect some microorganisms able to survive in these special conditions. What about the injection of 100 ppm of oxygen? So it's the same story. Sulfate reduction, okay, we inject oxygen, so we have a reoxidation of sulfide. So we still have sulfate. You can see that there was not decrease of sulfate anymore. So that means even with 100 ppm of oxygen, we have a toxic effect on the sulfate reducers. Okay, but what we can see on this figure is not so toxic that all the microorganisms disappeared inside the system. We have another equilibrium. And with this other equilibrium, it's still possible to have a degradation of hydrocarbons inside the system. Thank you.
Thank you very much, Anthony, for all these results. Do we have a question? Do you want that we develop a specific point on what was presented? We are available. Good. Nothing from the chat?
So I'm going to continue with my first idea about the sulfide. We proved with a model and with microbiological experiments that we have a consumption of sulfate by sulfate reducers and a production of sulfide. Okay, and so we have a decrease of the quality of the gas stored inside the UGS. My idea or my question is, with the mesogenesis, we can see an increase of the pH, and you know that for sulfide, everything is in equilibrium with the pH. So we have H2S, HS, and S2 minus. Yeah. So the idea is it's possible to move this equilibrium and to decrease the concentration of H2S inside the gas. So for the moment, it's just an idea. We need to check about that.
No, I think it's very unstable.
What?
This would be a very, very unstable situation.
What part?
Because if you change the pH again, then you have a huge H2S production.
Yeah, sure. And it's the same thing about the dissolution of minerals, because in the first part we can see a dissolution of product. So we can talk about calcite for the carbon source. We can talk about barite for sulfate source. But at the end, if you have an increase of the pH, you will have a precipitation of carbonate And so,
Okay, thank you. And our last presentation will be with Irina. Tac. I don't know if you prefer this or this. This? Yeah. So Dr. Irina Sin is working at Lemine Paris. Her research activities focus on multi-phase flow and reactive transport modeling. She has been developing reactive transport codes and studying coupled processes in the gas storage, the geological storage of CO2 with impurities, and uranium in situ recovery, but also on the development of reactive transport codes. Thank you.
Thank you. You can just click here. Yeah, great. Okay, I will present the work of the reactive transport group from Center for Geosciences at Paris, France. We'll talk about the reactive transport and what it can do for the underground gas storage. First of all, we'll look at the reactive transport. What is it? Then the phase equilibria, which is necessary to model the underground gas storage. And then, so we will see what actually it can bring us when it's applied to a real gas storage. And for instance, what geochemical reactions can be induced by the injection of different interesting gases. And we'll finish with the perspectives of our group's projects. Okay, what's it the reactive transport? We have been developing the reactive transport code, which is called HyTech since 1996. And HyTech couples hydrogeochemical reactions, processes. And so this includes saturated, unsaturated, multi-phase flow in the porous media of single or multiple porosity. And in these fluids, the aqueous and gas species are transported by different processes like advection, diffusion, or dispersion. And this is coupled with the geochemical code, which is called CHES. Because once your species are transported, the thermodynamic local equilibrium is perturbated, so you need to equilibrate it again. We do that with a geochemical code, which includes not only geochemical reactions, but also can do with the description of the physical properties of non-ideal gas and solutions. Okay, and a little bit of we have also very exciting ongoing projects, developments on history matching coupled with mechanics, variable porosity due to geochemical reactions, and also chemical and mechanical clogging. Okay, so with all these features, we can model different applications of materials, natural and not, at micro to kilometer scale. One of the historical application of our team is the radioactive waste disposal. And for example, one of the recent research, this is experimental numerical PhD study on that discloses actually how geochemical reactions can induce cracking of the concrete. Another one historical application is, of course, storage of CO2. As you all know, CO, for example, is an illustration of a CO2 dissolved in the aquifer water, which evolves during the time of the storage. So, for example, this is a mechanism which is called convective mixing that can be represented if you can model precisely the phase equilibria between a vapor and liquid phases. So let's look at how can we do that in our code. We choose the asymmetric approach to model equilibrium of potential in gas and in the liquid phases. The opportunity that we have So we model the fugacity coefficients by well-established equational state models. For example, Penck-Robinson or other or from this family. The Henry's constant should be, of course, corrected according to pressure and temperature if you're dealing with the underground gas storage. And the activity coefficients are calculated by classical activity models from that are well known from aqueous geochemistry. Okay, so all this is good, but still we need to fit all these parameters in these wonderful models. So we need to do data acquisition. So we perform in the experimental lab in collaboration with the Center of Thermodynamics from Mainz, Paris. And we could enrich our database to fit our model, compare it with different codes like Frixie and others, and to calibrate it also with another experimental data. So, for example, here is the solubility of CO2 in water and in brine in a wide range of pressure, salinity, and temperature. And it shows good results comparing different models that we use. Same work was done for hydrogen in water and brine. Okay. So this is a short list of species that for which we did the calibration. Okay, so let's look at what can we do with all these wonderful models. I want to show you a study that we did for a pilot that took place in the Paris Basin around 35 years ago. So this is the gas storage, okay? And here it should be in red, but so important. So here is a cushion gas, okay, that should maintain the pressure and the storage. And during this pilot, the air with 8% of oxygen was injected, was used as a cushion gas, okay? So after 3 years of injection of the air, the gas and water were sampled at monitored wells here. And we can see this map, the evolution of gas composition at monitored wells. In red, it's oxygen, and you can observe that it just disappeared in monitoring wells. And in blue, you observe the CO2. Okay, so CO2 was detected around 4%. Also, when you see water chemistry, the pH drops from 8 to 5.8. Also, we observe the increase in sulfate concentration, potassium, calcium, magnesium. So, what happened? What are the key mechanisms? So we suggested this the sequence of these chemical reactions. Okay, once you inject the air with oxygen, oxygen dissolves in the aquifer water. So it provokes the dissolution of pyrite that releases sulfates, but also protons. And then the acidification of the aquifer water perturbates the host rock, including, for example, carbonates. And this releases calcium, magnesium, and CO2 that in the later can degas in the bubble. So then, based on this scheme, we built a batch model, okay, to represent this sequence. So what we can see that the model is good in how to say, in phenomenological way. It can quite good represent what we suggested. So this is the dissolution of the pyrite with the time. After 6 months, we observe a quite rapid dissolution of the pyrite. It's around 14%. Also, the pH decreases, the solid blue curve. And the CO2 in red here increases up to 30% after 6 months. So we calibrated our model based on other experimental studies and parameters that we found in other publications. So and we supposed, okay, this is a batch model. The system is closed, so that's why actually everything is overestimated. Because you have this infinite source of oxygen, so your your minerals can react infinitely. Okay, so we needed reactive transport. So we did it with a radial 1D model. So you imagine the homogeneous aquifer and you inject the gas in this radial geometry, and we trace the things as a function of the distance from the injection point, from here to here. So here you can see after 1 month the evolution of the air, or the gas saturation. Also pH drops, and the pyrite dissolves here in blue, okay, especially at the injection point. Also, you can observe here the oxygen profile. While you inject air, it's normal that the gas saturation curve corresponds well to the oxygen. And here you can observe the accumulation of the CO2, which is like pushed by the injection rate flow. After 6 months, we continue to the injection. We observe like a plateau of pH and the continuous dissolution of the pyrite in blue, up to 22%. And the profile of oxygen doesn't move. It's like nothing happens, but the accumulation of CO2 is continuous. And so if we consider this model, it would suggest that in 4 or 5 years, after 4 or 5 years of injection, all pyrite will be dissolved in the vicinity of the well. That was not observed, so we decided to calibrate the model according to the field data. We decreased the kinetics of the pyrite, and this is presented by the dashed curves here. What we observed that actually the oxygen can advance further, okay, while the air is injected, okay. So the profile of oxygen corresponds quite well to the propagation of the gas plume, and the pyrite dissolution was decreased by it is homogeneously like the pyrite is dispersed over this distance which is covered by the gas bubble. So it's normal, yeah, we decrease the kinetics of pyrite, so the consumption of oxygen was slowed, and the oxygen can advance further, deeper in the aquifer, and this is a typical example of the competition between the velocity, Darcy velocity, advection, and the velocity of geochemical reactions. And this was analyzed and confirmed by the analysis of Doppler number, which checks the ratio of the reaction time and advection time. So with using this kinetic model, we have a reasonable value of CO2, it reaches 3%. So we say, so we need also to take into account the gravity effects. Yeah, we tried a radial model, but actually it didn't work well. If you're interested, you can read the paper. And we just did a 2D model, cross-section geometry. Okay, we imagine the natural gas in situ, just seated here in the red. You inject the cushion gas, which is here presented by the air. And after 6 months, this red area presents the injected air. here we can observe the same accumulation, like the same behavior as a radial 1D, the accumulation of the oxygen, they attacked pyrite, also carbonates, and they produced CO2, which is accumulated and pushed deeper in the to the border of the bubble. Yeah, and pH is quite representative, around 5.8. So the conclusion that the pyrite kinetics was actually is a key factor to calibrate the numerical model that controlled not only the rate of production, but also the distribution, spatial distribution of gases in the plume. And the impact of the radius of impacted minerals. So what was important also is to add transport mechanisms and to adapt the geometry. Okay. So this workflow showed us, yeah, we can apply the same thing probably to other gases. And this is just to mention that there are two ongoing projects on biomethane and natural gas mix injection. So as was mentioned by Anthony, the problem is that there is still a small quantity of oxygen which is present in the biomethane due to this separation purification process of biogas. So we need to discover the induced geochemical reactions by this small molecular oxygen. And yeah, and if you're interested, you can look at the presentation on the conference EDU. Also, this year we will start a project on hydrogen storage. The complexity is obvious for everybody, I think, today. How we'll deal with microbial activity, how can we calibrate our models. And not only, we will start, of course, by these beautiful experiments of Anthony's lab, but then how we will upscale this model to real sites. Okay, and and the last word. We acknowledge our partners of consortium PGT, Pôle Chimie Transport, that exists since 200. Which is a group of public and private organizations that supports high-tech developments and share the funding, scientific research, and expertise. We acknowledge greatly our historical, but also, of course, permanent partners. Thank you.
Thank you, Irina. We can take some questions. Yeah, Arnaud.
Thank you, Irina. And I have a question to you and maybe to Anthony as well. You both presented models and works on hydrogen storage on one side, or plants, and on O2 for biomethane storage, which is actually today also a reality. As you said, it's possible up to 100 ppm to have O2 in underground storages. So we all look, when we look at hydrogen, we look at population and families of microorganisms that are in how you call that, that does not burn O2. And do you, if there is hydrogen injection in a storage that has hold biomethane and O2, is there new families of microorganisms that could also use O2 and H2 to create new products?
You know that in microbiology, we said that everything is everywhere, and after the nature will select. So it's completely possible. I think that Martin said this morning.
Martin,
No, no. I mean, it's possible to have some microorganisms in dormant
Definitely, yeah.
condition.
Definitely, it's not only the hydrogen using or oxidizing microorganisms. There is a number of other bacteria inside the reservoir also sitting waiting for some, electron acceptors or donators or whatever. So the heterotrophic organisms, for instance, we didn't talk about that because that are not related directly to hydrogen, but they are working with oxygen and can be activated by oxygen in introduction, for instance. So there is other groups we did not talk about today, but if you inject other things, other chemicals, other gases, then other reactions can take place. There's plenty of bacteria sitting there, just waiting for something we give them to eat.
Yes, and there is a lot of things that we don't know still. For example, the genus of Pseudomonas. In our experiment, we are able to detect Pseudomonas, and so Pseudomonas is able to breathe oxygen or to breathe nitrate. Okay, in this kind of ecosystem, we have no oxygen and we have no nitrate. So before, when we detected this specific microorganisms, we said, okay, maybe it's a contaminant. Now, actually, in this moment, in the rings reactor, we are able to cultivate Pseudomonas inside the community, and we are sure there is no oxygen and there is no nitrate inside. So that means there is another thing, another metabolism for this kind of microorganism. And moreover, if you talk about Bacillus, for example, Bacillus is completely aerobic microorganisms, but this kind of microorganisms are able to do spores. And so when you are going to inject oxygen inside your system, so it's a non-toxic ecosystem at the beginning, and you add oxygen, and it's possible to have some aerobic microorganisms, and it's not contamination. They are there.
Do we have some other question?
I've got a chemical question. You mentioned that you measured the gas at the beginning of your modeling. Did you do any isotopic measurements to prove that this is thermogenic CO2 and not biogenic?
It's a very good question. So we don't have how to say factual report, because the pilot was done 35 years ago, and we know that this analysis was done. Also, we also thought about different sources of CO2, of course, and then we found there was another pilot of injection air injection, and then they also observed some peaks of CO2, small peaks, and it was in United States, and they did the isotopic analysis, and they proved that it comes from the calcite and the host rock. It's a good question, yeah. Thank you.
Another question here.
Thank you, Patrick Egerman, Storangi. So sometimes with two problems, we can make a solution. So I must confess it's not always the case, not often, but in our case, so we have to deal with two new gases, hydrogen and oxygen. So we have shown that both can be reactive. So hydrogen can promote hydrogen loss, sulfide formation, and so on. And on the other part, oxygens, it seems that when we put some traces of oxygen into the system, so we put in stress the bacteria, anaerobic bacteria. And so my question is, if we consider in the future hydrogen stream with traces of oxygen, can we remediate somehow to what we discussed today?
Probably I didn't understand the question.
Yeah, maybe I can repeat or summarize. But the idea is when we put oxygen in an environment, we have discovered that sometimes we can disturb the bacteria that are inside and stop their reactivity. So we can imagine that in a system where there is hydrogen and a lot of bacteria that we would like to avoid, maybe we can add a little bit of oxygen to avoid all the reaction of sulfate-reducing bacteria and methanogenesis, etc. Yeah.
Small amount of oxygen, I guess. Yes, it was, I think, that the idea of it. It's complicated to predict because for this we need some lab experiments. Because there is a theory. I can give you numerical results or whatever you want, but then I'm not sure that I will take the responsibility of these results if it's not fitted on the lab data.
And Anthony, I was wondering, you did not try to mix hydrogen and oxygen and do a test with some bacteria?
No, because we have a problem of risk of explosion. But
Yes.
in another life, I worked with what we call null-gas bacteria. So for the growth of null-gas bacteria, we need a little bit of oxygen, hydrogen, and CO2. And so it's possible to have growth and consumption of hydrogen with this kind of microorganisms in micro-oxic conditions. Patrick, what I propose is a new project with sulfide and oxygen. But on the paper, it's a good idea. But
Also, I think that it highly depends on the definition of small amount of oxygen, because we can deal with suboxic conditions or highly oxic conditions, and for this influences a lot the system. Even for example, for the sulfur, it's complicated to control the proportion of oxygen.
So I would like to move on the technical challenges now. So as you have seen, so the laboratory tests that we have made highlight a lot of issues that could happen in the underground. And there are some specific topics that I think it would be interesting to discuss together now. The first one is the idea to move from, the laboratory test to something on site, on field. How we pass from the laboratory scale to the on-field scale. What are the representativity of what we do in the laboratory? So maybe I can start with you and Catherine. So during your test, how do you think it was representative from the underground? And if it's not totally, what are the difference between what was done on the lab between the underground?
So I think for our problem is mostly that we just did low pressure, and we just don't know what will happen in the high pressure yet. So it can be both ways. Can go up or it can go down. I don't know. It was with you guys that we had the discussion. It will go down, no? Yeah. Once before. So if someone else wants to continue with this.
For us, inside our project, we tried to be the closer possible to the ecosystem. So we use the formation water with indigenous microorganisms. We use the rocks from the targeted side, but at the same time I didn't precise before. We use inside the agitation inside the high pressure reactor. It's in order to be able to decrease the time of incubation because we plan to do two experiments each year. So it's not possible to have incubation during 800 days or 1,000 days. So it's not possible. But at the end, what we can say, it's our results is similar to what we saw on the Lobodice storage. So I think it's quite close, but we have the agitation. So
It's similar but faster.
yes,
Mm.
yes, I think.
So for the salt cavern I was talking about, where we had 6 months of incubation, so what they found is, so in the beginning they loaded with 100 bars hydrogen, and in the end 98 bars came out, but they couldn't measure any sulfide. And now what I did, it just at low pressure so far, but yeah, I produced a lot of sulfide in just 3 months, so there's difference, definitely.
Yeah. And so when we want to pass from the lab to the on-field, so we need to implement an upscaling factor. So in Hystories project, we presented this morning that to pass from the laboratories that were done in a MicroPro laboratory to the modeling of 3D storage scale, we used an upscaling factor of 10 power 4, I think, something like that. But this factor was fixed quite arbitrary, based on the difference of volume, but also based on the difference, like in the laboratory we are in optimal growth condition, whereas on the site it would be starving condition. The porosity would not be the same, but there is a lot of difference between the different factors that can be estimated or fixed. I think in Lobodice it was quite different also. Joachim, I don't know if you remember, it was a factor of 50, so we can see that on a specific case it can be a factor of 50 to pass from lab to on-site, and on the other one 10 power 4, so quite a huge difference. And I know, Irina, that in your model, to calibrate it from what you have observed on site to your modeling, you need also to implement a factor.
So this was a complexity that when we calibrated our model according to lab experiments, that was done for another project, but similar mineralogy, and the parameters was in a good accordance with other publications. We observed overproduction of CO2. All reactions were too fast, so we applied a field factor of 10, which is not so big because we also saw a factor of 10,000, or usually it's around 100 and 1,000 between, in this range. And it's normal because in our models everything is it's an average approximation. So in natural media, your pyrite is covered by other minerals to have the access to the reactive surface of minerals. It's okay when you are in the lab, because everything reacts instantly. But in the nature, you have a passivation, mechanisms, other things. I guess it should be the same, but with bacteria. But you say that they are everywhere. Is it everywhere, like everywhere, or you need also to take into account this upscaling to natural conditions? And also, I guess that when your microbial community grows, it cannot grow to infinity. So you also should observe a plateau, like we all know from Manage, like a model. And is it a plateau that we can really predict from experimental results?
Yeah, this asymptote.
Yes, so we work with very, very specific environment, close environment. So it's not like an environment of the surface where it's possible to have some nutrients from another source. Here, it's a closed environment. So I think it's we have a maximum quantity of nutrients for a limited quantity of microorganisms. So I mean, for your modelization, for example, for a microbial growth, we modelize in general an exponential growth. But the growth of the microbial community won't be exponential. At the moment, we have a limitation from the ecosystem. I mean, for all our experiments, all the time, the maximum concentration was 1 million of cells per milliliter. And there is not an increase of this population. So, I mean, it's possible to have a consumption of hydrogen, but I think if the industrial are okay to have a limited loss of hydrogen, I think it's possible to have this storage of hydrogen. It's not a huge machine to produce hydrogen sulfide or methane. I think there is a limitation.
Yeah.
And if we don't add artificially inside nutrients, at the moment we have a limitation of the system. So I don't know, Martin, if you are ready.
And yes, so from what we have discussed, so we see that the upscaling factor could go from 10 to 10,000 depending on the case. So I think we all agree that we would need more pilots to calibrate this upscaling factor in the future and to get some better prediction in our model. So there was another topic that I wanted to discuss also. It's about what was presented this morning by Martin, the bacteria reactivity assessment risk. So you can see that we have tried to develop the risk of microbial potential depending on some parameters that you can see here. So we have the salinity, the temperature, the availability of carbon source, and the availability of sulfate ions. So I don't know, Irina, maybe you can start. In your opinion, what would be the best storage condition for hydrogen storage, and what would be the worst? Is it the same that what was presented in Hystories, or do you have different target?
I think that probably favorable conditions would be deeper storage with a higher temperature, higher pressure, and without carbonates and low content of sulfates, of course. So if you have a scent reservoir, it would be a good option. If not, probably high salinity.
Salt cavern, it's true that it's more interesting for hydrogen storage if you want to avoid a microbial reaction. And maybe, Anthony, I think you wanted to add some parameters, because these are the first one that you can detect, but it's not the only one.
Yes, I think, as I said before, I think we need to add some other parameters like nitrogen source, for example, or phosphorus source, because you can add an infinity of energy source like hydrogen and carbon source like CO2. So on the paper we have a growth of hydrogenotrophic microorganisms, but at the end, if you have a lack of nitrogen, for example, it's not possible to produce some proteins or to produce nucleic acid, and so you have no growth at all. So I think we need to have some other parameters. For example, I'm not able to explain why at a moment during the second experiment with the second aquifer, the consumption of hydrogen was stopped. There is something inside the reactor, so you can say, okay, it was in batch, it was across the ecosystem, so yes, but the time is not so long, because I think it was 60 days or 70 days. It was nothing. If we compare with your condition, it was nothing. We put inside the rock, so it's a source of metals. It's a source of organic compounds too. It's a source of a lot of things, and something stopped the consumption of hydrogen. So I think there is something else. And maybe the second thing to say about this scheme is you talk about a risk for the production of sulfide. So the production of methane is not a risk. Is a risk of the storage of hydrogen. So yes, it's not corrosive, it's not toxic, or not so toxic if you compare with the sulfide, but it's another kind of risk. And the last thing is everything is everywhere, but in 2 experiments we didn't have a lot of methanogens inside our experiments, so maybe that everything is not everywhere. So.
Yeah, that's a really important point, because it means you can have a storage with a low salinity, an average temperature, with carbon source and sulfate. But if there is no bacteria inside, you can still use it for hydrogen and it will be good. So it's really important to characterize also if you have or not bacteria in your site-specific storage.
Maybe a point to add is the systems are not closed, so there can also be input from outside, charging or withdrawal, and you never know, maybe it works for 1 or 2 years, but then someone can come into this environment which is adapted and everything is going downhill. I think this is also an important point.
Yeah. And Anne-Catherine, there was the point that I think we did not develop it too much in this microbial risk. It's the risk of biofilm formation that was not so many studied in Hystories, but will be more in HyUSPRe. Maybe you want to add something on this?
So far I didn't see anything about biofilm. Maybe Martin, I don't know if you saw ever something like biofilm related. This was like, we never saw something. For like, even like, I don't see even density, like I see activity, okay, but I need to look under the microscope that I can see, okay, there are cells inside. I don't get anything dense.
So you mean in all your tests you have never seen a formation of biofilm for the moment?
Even not that turbid.
So it's quite reassuring.
Yeah, but I guess it's also like the temperature in the reservoir is higher, for example, but in the tubing, what's there? So if you get the biofilm accumulation and the tubing is lower temperatures.
Yeah.
I don't know if it works, but biofilms is a special topic. So there is, you know that there is bacteria which tend to form biofilms and others not, and what we detect in our samples, in our downhole samples, is only the bacteria in the liquid phase. We don't sample biofilms from the reservoir. It's not possible at all. So and even we just, what we talk about here today is when we talk about the microbiology, is only a small picture of the whole image of a reservoir. We just have maybe 1 or a couple of wells in a huge reservoir. We just take tiny little samples and try to model a huge reservoir. That's a difficult thing, I would say. And so there is zones in the reservoir around the wells. There is zones at the edges of the reservoir where we have a flow of water in and out the reservoir. We have mixture. We have supply of these components, nutrients, nitrogen, phosphorus, all the elements necessary for growth. This is a very basic sketch. I know there is plenty of other parameters we have to consider, and if one of these parameters limits the bacterial growth, then we don't need to talk about the other parameters. But Yeah, that's the starting point, and I'm very, very thankful for your input. So yeah, biofilms is a special topic, so don't start it like that today.
And
But in fact, in this kind of
Anthony, we
ecosystem,
don't have, yeah, just quick. Yeah, but, no, you can go quick.
the biofilm is the main form for the microorganisms in deep underground, in deep aquifers. Because we work with a microporous ecosystem, and so it's not like your flask. In your flask, the major physical condition is convection for the fluid, or for the microporous system, it's not that. And so when we work with micromodel, microcapillary, the first thing that we can see that it's a deposit of microorganisms inside the microcapillary.
Yeah.
So, but it's not a biofilm with a lot of risk for the storage, because we don't talk about a matrix, a gel matrix with clogging, this kind of thing. So it's two kind of biofilm.
So that you would suggest that a biofilm or growing biofilms would be more in the front of on the periphery of the gas pool.
What do you mean by biofilm? Because if it's
Sorry, we cannot continue to talk about biofilm. Otherwise, we will not have the time to talk about our last topic. So the idea is, so we know what are the best kind of storage to consider hydrogen. So we are talking about salt cavern. We are talking about porous media, but with not so much carbon source inside. But if we want to implement an hydrogen storage in a place where we know that there is a bacteria risk, what could be done? So we have presented this morning some bioseed solutions that could be implemented, but we think there are some limitation about this biocide ID. I don't know if one of you would like to start discussing about what are the issue about biocide injection in the underground.
I think the first problem for the biocide, if we talk about salted cavern, it's not a problem. It's closed.
Because it's a closed...
Yes. If we talk about depleted reservoir, I can imagine it's okay. So, but about the deep aquifers with water, I think maybe it will be complicated because of the law in France. So I don't know for other countries in Europe, but it's difficult. The second thing, I think that Martin talking about that, is our capacity to inject the biocide inside the microporous system. And so it seems to be very complicated. So I don't know about that. And the third thing is maybe the biofilm. Because it's different to use the biocide in order to destroy planktonic cell, and use the biocide to destroy biofilm, because you need to use a huge quantity of biocide for the biofilm.
Do you want to add something? No? Okay. Yes, so we know that biocide is limited. We can also consider change of pH, as we have seen this morning. To increase the pH would limit the bacteria reactivity. But it's the same. We need to check that this increase of pH will not disturb the rocks and the ground, or some dissolution that could happen. So yeah, actually there are two solutions. You can try to treat underground, or you need to predict something above ground to treat it when the gas is withdrawn with some impurities. Okay, so I think we are at the end of our panel session now. So once again, I want to thank you, all of you, for your presentation and the discussion. And I think it's time for a break now.